You are listening to Talking Machines. I'm Catherine Gorman.
And I'm Ryan Adams.
And we are bringing you our second episode. We are so excited about it. And we're going to start off the way that we hope to each week with discussing a little bit of news from the field. And Ryan, you wanted to talk about a paper that you saw at NIPS, which actually won an award for being one of the best papers this year.
Yeah, that's right. So it's a paper called A-Star Sampling, and it's by Chris Madison, Danny Tarlow, and Tom Minka. And, you know, and like you said, won one of the awards at NIPS. It received an oral presentation. I think it's cool because it's a generalization of a really fun little trick in machine learning and probability. And, you know, machine learning and statistics and sort of related fields are full of cool little tricks. These are sort of interesting ideas where you sort of take a bunch of simple things, you sort of put them together in an elegant way, and then something a little bit surprising happens. I think the most famous one of these is something called the kernel trick that gets used in a lot of different areas of machine learning. And they kind of tickle your brain in a funny little way that mathematics doesn't always do. I know it sounds funny, but I almost
You're
liken
making it sound like a Muppet, Ryan.
Well, I think of it more like a really, you know, I liken it most directly to something like a kinetic sculpture. Like there's, you know, Arthur Ganson makes these like super cool sort of kinetic sculptures, and they're like a bunch of simple devices put together in a surprising and interesting way that kind of makes you think, oh, well, that's pretty cool. I can't believe that all
That's a giant monster moving down the beach.
Well, I can't believe that all sort of worked out. You know?
Yeah.
And there's a few different kinds of tricks, and this paper is about generalizing one of these tricks. And the specific trick that it tackles is about sampling from probability distributions. Mm-hmm. That's something we do a lot in machine learning because we're always modeling uncertainty, and so we like to use probability for that. And the way that we normally sample from probability distributions is we sort of do what I think of as kind of a dartboard method. Mm-hmm. So the idea is that we have a computing tool that will throw a dart uniformly at a dartboard. And then what we do to sample from a non-uniform distribution is we color the dartboard, say, into different regions, and we make the regions larger or smaller in proportion to the different possible outcomes.
Got it.
And then when we throw the dart, then we look and see what region it hit. Mm-hmm. Okay, that seems kind of straightforward, and we spend a lot of time on our computer simulating from that. The trick that this paper discusses is a totally different way of drawing samples from a discrete distribution.
Oh, wow.
And this is going to sound kind of weird, but imagine rather than throwing darts at a dartboard, imagine we have the dartboard we care about, and what we're going to do is we're going to construct an imperfect copy of it.
A dartboard we don't care about?
Well, no, we're going to care about this one, but we're going to do something different. We're not going to throw a dart at it. What we're going to do is we're going to pick the largest region. And we're going to call that the sample from the distribution. And the idea is that the imperfection that we introduce when we make this corrupted copy is going to maybe sometimes make some of them bigger, some of the regions smaller. And the idea is then that by picking the best one, the biggest one, then that's kind of has some randomness in it due to this corruption. So imagine a process where rather than throwing a dart, what we do is we take the dartboard we care about, that's like kind of an original pristine one, and then we're going to corrupt all of the kind of sizes of the regions and create a new one, and then we're going to just pick the biggest one.
Oh.
And that's going to be the sample from the distribution.
Huh.
And it turns out that if you sort of specify a particular distribution for this corruption, something called the Gumbel distribution after a guy named
That is a great name.
Yeah, I know, after a guy named Emil Gumbel. So it turns out if you use this Gumbel distribution to do the corruption, then it actually recovers exactly the same distribution as the original kind of like throwing darts procedure. So it's like a totally different idea, but that gives you the same answer in the same distribution. And the reason that's interesting to like computer scientists is because it replaces this kind of sampling procedure with a maximization. And so rather than sampling, we're optimizing. And optimizing is like a completely different kind of thing most of the time. It's more like searching, basically. And there's a different bag of tricks, and a lot of those tricks wouldn't typically apply in the case where you just wanted to draw samples. So it's a kind of a surprising connection where there's this totally different way of generating samples. And so that tickles my brain. I think it tickles some other people's brains, maybe. And I sort of call this the Gumbel Max trick. And so this paper explores a variation of that, in which you, instead of just like discrete regions of the dartboard, you can do this trick with an infinite number of regions, a continuum.
Got it.
And deal with continuous random variables rather than just discrete random variables. So I thought it was super fun and creative and an interesting thing to learn about.
So does this new tool have a name unto itself? Is it the Max Gumbel Maximus?
I don't know. I mean, they created this thing, I think, that they call a Gumbel process.
Okay.
In statistics and probability and machine learning, when we take something that sort of has a finite number of, say, random variables, and we generalize it to having an infinite number of them, then we often take, instead of calling it a distribution, we call it a process. So there's a few different things: Gaussian distribution versus Gaussian process, and Dirichlet distribution versus Dirichlet process. And there's a lot of these things like this, and they sort of invented the idea of at least explored the idea of a Gumbel process.
Cool. Well, it sounds really interesting, and we'll have a link to that paper on our website so that you can read the whole thing and explore the process for yourself. And Ryan, I was trolling around the internet like I like to do earlier this week, and I came across this paper letter, I don't know, community discussion.
It's like an open letter.
It's like an open letter. It's called Research Priorities for Robust and Beneficial Artificial Intelligence. And it's basically a letter where a number of researchers have outlined sort of, I guess, best practices or ideas about best practices for how we continue to research artificial intelligence. And it's been gathering a lot of signatures, and it's raising some really interesting questions, I think.
Yeah, it's really interesting. I mean, there's been this kind of conversation that started, I think, with like Stephen Hawking and Elon Musk lately, and it's such a big topic that I think we need to have a whole episode about it.
Yes, definitely. We're going to have an entire episode devoted to these very deeply seated questions in machine learning and artificial intelligence later in the season. So stay with us for that. But right now, you can head over to our website, talkingmachines.com, and read it for yourself and come up with your own opinions.
Yeah, it's definitely worth a read.
So here on Talking Machines, we like to field your questions and then give you answers as we best can explore. And this week we've got a question from a graduate student at the University of Texas in Austin, Shiva. And Ryan, I'll play you his question.
Hey, Catherine and Ryan. The Talking Machines podcast is a great idea, and I'm excited to see how the series unfolds. I am Shiva, a graduate student pursuing my PhD in particle physics at UT Austin. I've come across a little bit of machine learning on the web mostly, or through friends in computer science, and I thought I'd ask something basic that I don't fully understand. It seems to me that, based on the examples I've seen, what's typically called machine learning involves the computer optimizing parameters in some model, while the model is actually designed by a human being to capture some structure or features in the data. So in what sense is the computer actually learning anything about the situation, since it seems like the essential work is actually done by the human?
So Ryan, he's got a really good point. At what point do I stop programming and the computer actually starts learning something?
You know, this is a wonderful question for a lot of different reasons. And part of the reason that it really resonates with me is because it expresses a certain kind of disappointment in artificial intelligence research and machine learning research. When you sort of like look under the hood and you learn more about it, then you discover that it's not magical.
Right.
Like we really want, and I think this is kind of driven by science fiction and kind of different media that involve a distant future with super intelligence.
Jetpacks.
Yeah,
hoverboards.
Hoverboards and all this stuff. And I think, we have an idea of what AI should be like, and it should be something that's very difficult to understand. And so once we understand how to categorize it within kind of our existing fields of knowledge, then it's not so fun. And it just turns out that all it is optimization framed correctly, or all it is Bayes' theorem framed correctly, or search framed correctly. It's all about setting things up and then applying techniques that we do understand. Like I said, this really resonates with me personally. When I first encountered artificial intelligence as an undergrad, I was super excited about it. Yeah. Then I took the course and I was like, man, this is just search. and it was, it's a huge disappointment. You think you're going to learn deep secrets of the universe, and you just sort of learn algorithms that don't seem so crazy. Yeah. And I think sometimes in machine learning, people say, well, this turns out to be just statistics, or it just turns out to be, optimization and so on. So this is sometimes expressed as a certain kind of curse of doing artificial intelligence research, in which the goalposts always kind of move, because as soon as you develop something that seems very intelligent, some algorithm that can solve some previously very hard problem, then all of a sudden we call that known, and we tend to say, now that's not AI. AI is the thing we still can't do.
You got there, so how could this possibly be the thing we were trying to achieve?
Yeah, AI is the kind of computing that we can't quite do yet. It's never the thing that we can do. And so even if you think about systems that we're used to interacting with now, and we think about whether they were available, say, 15 or 20 years ago, if we showed ourselves Google,
Right.
from 20 years ago, that would look like AI. You would say to yourself, wow, that's amazing. So you have this system where you can just type in questions and expect to get answers, and it would just do that, and it sort of understands natural language to some extent, or where you have a pretty robust speech recognition, or really good face detection.
Yeah.
You have all kinds of fraud detection online. Lots of systems that we interact with every day would be artificially intelligent by a definition of not, according to the standards of not that long ago.
Yeah.
And this happens over and over again, right? Like, we don't consider now solving chess to be a sign of artificial intelligence.
Right.
But if you were in the 1950s and said to someone, what will be the hallmark of having achieved artificial intelligence, a lot of people might have said, well, as long as it can, if it can beat Garry
Kasparov, that thing's got to be pretty smart.
Yeah, exactly. And yet now we sort of decided that actually that's like a
right,
kind
it
of
doesn't count.
It's kind of weak AI is what the way we often talk about this in the field is talk about weak AI versus strong AI, where strong AI is this mythical thing that sort of is like human equivalent intelligence. This dynamic in which we're faced with interesting, very challenging problems, and then we figure out how to solve them in the name of AI. Sort of always results in us not calling those problems AI any longer, and a lot of those problems feel a lot like optimization, to be sure.
Yeah.
So I think it's really worthwhile to try to be clear and kind of remove the mysticism from this area and from machine learning and try to identify what it means to learn something. And I think one very nice way to think about learning is that to learn is to examine a space of hypotheses. So there's a lot of different ways that the world might work. Maybe this is something like mapping images to labels like dog or cat, or maybe it's understanding structure and natural language, or a lot of different things. But ultimately, we have a space of possible hypotheses for the way that the world works. And then what we do is we get some data, we get some experience, and then we try to figure out which of these hypotheses is consistent with the data that we've seen.
Yeah.
So so we define this space, and then we pick the best one, and we're done, right? That's all there is to it. So
finished.
And that picking the best one business often has the flavor of optimization, right? Now sometimes and it's not always true. Sometimes what we do is we consider a lot of different hypotheses and try to average over them, and that's kind of what the Bayesian machine learning story is about. But sort of framing the problem as being as simple as specifying a hypothesis space and then searching over it in some way misrepresents whether or not it's easy and possible. Right. Just specifying the hypothesis space itself turns out to be a huge challenge, and in fact, like what this whole game is about. And it's true that humans often have a lot to do with trying to figure this out, and we call this the kind of coming up with the inductive bias. So what is it about the world that I am able to learn? So what is the kind of structure that I'm willing to generalize when I see some? I've seen a bunch of examples before. What was important about those that I'm willing to sort of connect to some new example. And we can do this in a lot of different ways. We can put preferences on these different hypotheses or restrict the space and so on. But the reason that we do this and that it's not trivial is because there's no free lunch. In fact, there's something called the no free lunch theorem that just basically corresponds to the fact that you have to make structural assumptions about the world in order to succeed in this. And that if you assume absolutely anything, then you can't learn.
Right.
And this shouldn't disappoint us, right? This shouldn't cause us to feel like suddenly actually learning is trivial. And this is because these assumptions are totally necessary, and intelligent natural systems like people and dogs and fruit flies all make structural assumptions about the world that enable them to operate.
Yeah.
And they, you kind of assume that you have a natural intuition about physics that enables, a baseball player to catch a ball, that the ball doesn't just stop and zoom off in some other direction, right?
Right.
And the weatherman can kind of make reasonable predictions about the temperature tomorrow because it's probably not going to be that different than the temperature today.
Yeah.
These are structural assumptions that we feel like are kind of okay and are associated with being intelligent.
Right.
So it doesn't bother me so much that we need to come up with an inductive bias to do anything in the world. And then this other sort of aspect is, the optimization, the how do I pick the best hypothesis. So machine learning is a big consumer of optimization. And in fact, to such an extent that a lot of machine learning researchers sort of build their whole careers around optimization specifically. Many papers in machine learning are trying to contribute ideas that are general purpose optimization techniques. I write papers about Bayesian optimization that are meant to be pretty general purpose, and we find use for them in machine learning, but it's not the end of the story. Finally, it's worth sort of thinking about the fact that even coming up with a useful sort of family of these inductive biases, even sort of identifying interesting structures and giving them to the algorithms sort of a priori, still doesn't make this kind of like an easy or uninteresting thing.
Right.
I mean, consider the fact that the human brain has had millions of years of evolution, and a tremendous amount of that evolution has been about building in all of this structure so that you can learn about things in the world very rapidly, whether it's linguistic structure or visual structure, or auditory structure, spatial structure. These are things that your brain is extremely well suited to be able to learn because of this kind of bias towards this, because this is the kind of stuff that really exists.
Yeah.
And yet that doesn't make the ability of your brain to learn sort of less impressive, like within a single human lifespan. And so we don't find ourselves thinking that the brain is any less interesting as a device simply because it's been preloaded by evolution with so much interesting stuff. I'm totally sympathetic with this kind of like disappointment that it's not magical, but the fact that when we peer under the hood, we can frame it in terms of mathematics that we understand, it doesn't
sort of
make
makes it more magical.
It does. You're right. It does make it more magical, but it certainly doesn't make it easy, and it doesn't make it less important.
Yeah, definitely. Well, Shiva, thank you so much for your question. And if you have a question you want us to try and tackle here on Talking Machines, you can get in touch with us on Twitter. We are TLKNGMCHNS.
That's super easy to remember.
It's super easy to remember. You just take our name and take out all of the vowels. I thought it was very clever at the time. Or if you want to spend less energy on spelling when you reach us, you can get us by email at thetalkingmachines@gmail.com. So send us your questions. So like we mentioned to you in the trailer episode, we went up to NIPS last month and we got to do all of these amazing interviews. And one of the people we got to sit down with was Ilya Sutskever of Google. And Ryan, can you tell us a little bit about his work?
Yeah, Ilya does tons of really cool things. And he was a PhD student at the University of Toronto when I was there as a postdoc. And I've just always been blown away by the creativity and the depth of understanding that Ilya has, but also his sort of evangelism for the deep learning view. And so it was really great to sit down with him and get his take on kind of what's important about a lot of these different ideas.
And when we talked, I asked him first how he became interested in the ideas in machine learning and artificial intelligence.
I was always interested in artificial intelligence as a teenager. I thought it was very nice and fascinating. And then I went on to study mathematics as an undergrad. And when you study math is very much about proving things. It's very much about if you see a certain pattern, it doesn't mean that it will be true unless you prove it. And so learning seemed to be very counterintuitive to me, coming from a math background, because learning is all about making these inductive steps, which seem to be impossible to justify from a rigorous approach. If you are used to rigorously proving results, induction seems almost like magic. So I was interested especially in learning because of that, because I knew that humans do it, and it seemed impossible from a naive mathematical view that learning seemed impossible to me. And so I looked around, and it turned out that Toronto had a very nice, very strong learning group, and I started working with Jeff Hinton while I was still a second-year undergrad. It really is the case that machine learning is not a complicated science. It's not like physics, I think. I think that in physics and math and a lot of these other hard sciences, there is a lot more ground needs to be covered before a person can start to be useful. Although I'm not sure because I've never done this. This is my impression. Whereas machine learning is a lot more the ideas, the important ideas, even the ones that are related to cutting-edge research, are very close to the surface. It doesn't take many years of study to be able to understand the main ideas behind machine learning and the main ideas behind what works and the main intuitions with the right guidance and direction.
So can you tell us a little bit about the research questions that you're working on now?
Yes, so I was working on supervised learning. So supervised learning is the most successful aspect of machine learning by far. It is a certain approach to machine learning where you say that you've got lots of input-output examples of a certain behavior you want to imitate. And then you take those input-output examples and you give them to your machine learning algorithm, and it undergoes a process of learning, and when it's done, it understands, to some extent, the patterns that are in those input-output examples. And then it can imitate this behavior to new examples that are not in the training set. So let's say you want to recognize and to determine what's the object in a photograph. So this is something for which it is relatively straightforward to generate a lot of input-output examples by asking humans to look at an image and to tell us what's in it. Then once we have enough data, we can give this data to the model so that it will learn to imitate this behavior. The thing that's really successful is supervised learning with large deep neural networks. Now, there's a very specific reason why it's successful. It's because large deep neural networks can perform all kinds of very complicated computations. And so when you use supervised learning with large deep neural networks, what you're really saying is the following. You're saying, give me the best possible neural network that can imitate this behavior. So of all possible neural networks, some of them imitate this behavior better than others. So the neural network, by the way, so when I say different neural networks, I mean that the connections on the neural network, they determine different behavior. If you change the connections, you change the behavior. And so the question becomes, what are the best connections? So you say, okay, the data will tell us the best connections. Because the deep neural network is such a powerful, it's such a rich model, it can do so much non-trivial work. It's very hard to imagine what kind of things it cannot do. Because of that, whenever we have a large data set, we can apply a simple learning algorithm to find the best neural network and get good results. So I was working on extending the supervised learning approach of neural networks to the supervised learning problem where the input is a sequence and the output is a sequence. So this is really, conceptually, it's not different from what I talked about before. It's mainly a technicality. It's making sure that the model will know what to do when the input is a sequence whose length is no longer fixed in advance, and the output is also a sequence whose length is no longer fixed in advance. But it is the same basic approach, and it uses the same basic learning algorithm. And so, again, because these models are so expressive and powerful, they can really solve a lot of difficult, non-trivial pattern recognition problems, and problems that would be almost unimaginable to solve by any other means. And again, it's what's so surprising about it is that even though the approach ends up being so powerful, it truly is extremely simple to understand. The learning algorithm is extremely simple. It would take a smart student only an hour to understand why it all works.
So do you find that that's true, Ryan? Do you find that the basics of machine learning are sort of easier to get to and to begin to manipulate than, say, in physics?
I guess I'm not sure that I exactly agree about how it relates to physics, but I think I do agree that it's that the basic ideas are straightforward, especially supervised learning, where as long as you can talk about what it means to do well on a task, as long as you can write down what we call an objective function, that is, where sort of say maximizing this objective function corresponds to doing better. In this case, it's exactly this successful imitation that Ilya is talking about. As long as you can sort of write that down, then there are a variety of interesting tools to think about. To think about how to improve it, how to do the learning, which is then going to be maximizing that objective function. I think neural networks, people imagine that there is a lot of magic going on in them. But I think Ilya would agree that they're actually not magical, that they have a kind of a weirdly bad reputation, perhaps because of the word neural. But in fact, what they are sort of function approximators. They're adaptive basis function regression is the way that I think about them. And that's something I think we can all agree is a good idea and not magical. I don't know, Ilya, do you have a...
So neural networks have two parts to them that make them work. One of them is not magical, but I think one of them is quite magical. So neural networks because they are large and deep, it is possible to arrange their connections so that their neurons will compute all kinds of complicated things, which, among others, often includes the solution to the problem we are trying to solve. Now, Ryan alluded to an optimization procedure, which finds the best neural networks given the data that optimizes our objective function. It is the optimization which is a little bit magical in the following sense. The neural network objective function is a very complicated objective function. It's very non-convex, and there are no mathematical guarantees whatsoever about its success. And so if you were to speak to somebody who studies optimization from a theoretical point of view, they would tell you that there is no theoretical reason to believe that the optimization will succeed. And yet it does. And this is an empirical fact. It is not something that theory has much to say about. And it is this part which is, it is not magic, of course, but it is poorly understood. We don't really know why our very simple optimization algorithm, which is fundamentally a heuristic, works as well as it does on these problems. Because there isn't a mathematical theorem, or there isn't a theory which says that it should succeed.
I think some of this has to do with a fairly limited definition of success that people in the convex optimization literature create, which is to say, are you guaranteed to find the global maximum or the global minimum for convex problems of this objective function? And I think the reality is that we have a loss function, and we have some way to measure whether or not things are working, and you can think of it, this iterative optimization process, as just gradually getting better. Mm-hmm. Now, the theorems that we would like to have are about the idea that I have the best one. But in no way is human intelligence the best possible intelligence, and any engineered system that we have that's successful for airplanes or cars or anything else, these aren't the best systems. We just want good systems. And the kinds of things that we get with deep learning and with non-convex optimization are perfectly good systems that may not be the best, but are nevertheless useful and interesting.
It's true, but if we go back in time to 2005 or 6, at this time, it was widely believed that the deep neural networks that we train right now with our simple optimization algorithm, which is called gradient descent or backpropagation, by the way, it was believed that, let's say neural networks with 10 hidden layers simply cannot be trained. And so it seemed perfectly plausible, and in fact this was also the empirical experience, that if you take a 10-layer neural network, you randomly initialize it, and you start doing backpropagation, you will not get any sensible result whatsoever. And that would also be perfectly consistent with what we expect from non-convex optimization. You could imagine that there is just so much complexity that there is just no way for the poor gradient to know how to get it off the ground, so to say. And yet over time, we discovered that actually the mistake that scientists were making is that they simply weren't paying enough attention to the scale of the random initialization. So when you train a neural network, I mentioned that it has all these connections between the neurons. And the connections have numerical values that determine their strength. And our algorithms, like Ryan said, they improve the solution. They're based on the idea of continual small improvements. But you need to start somewhere. And so typically, researchers would start with small random weights. And apparently this was simply wrong. Apparently you need to be very careful with the scale of the random weights. And if you're careful with the scale, then you will find the right scale. Or it turns out that it is possible in very many cases to find the right scale so that the simple backpropagation, the simple gradient, is able to improve it and to get it off the ground and to get good results. So there is, I still feel that it's a very fortunate situation that the simple gradient descent is able to train deep neural networks.
So this is something that I haven't heard somebody say out loud before. Maybe you've been saying it for a long time, but there's a lot of different intuitions that people have about what has changed since sort of 2004, 2005, or since the last time that neural networks were very popular in the machine learning community in the sort of early 90s. And there are many different choices that you have to make. So what's your intuition? Can you expand a little bit more about the intuition of weight scale as being the important thing? Now we're still talking about small random initializations, but maybe you mean extremely small random initializations, or I'd love to hear you talk more about this.
Yes, so this is a very good and important question. But you could actually ask two things. You asked about what changed, then specifically about the random initialization. So several things have changed since the early times. We have more data, more computation, and we know how to train these models. The scale of the random initialization is related to our ability to train these models. There are specific non-trivial things we can say about the random initialization. The way to think about it is that a neural network, it has all these neurons and connections. And the way it works is that you take your input and then you multiply it by the random connections, and then you do a tiny bit of nonlinear processing in the neurons again. So you got your input, you multiply it by the random connections, and you apply a small nonlinear processing. And you do it again by the next layer of random connections. You multiply it again by the random connections, and you do nonlinear processing again. And so what happens is that when the random connections are too small, as you keep on multiplying your signal by the random connections, it goes to zero, it decays. And so by the time you get all the way to the output, there is no signal. The output has no relationship to the signal anymore. And our learning algorithm is very, very greedy, and it can only notice, it can only improve things, it can only improve the relationship between the input and the output if there is an existing relationship in place. And so it is important for the random initialization to be large enough so that the signal doesn't decay, and so that by the time you get to the output layer of your neural network, changes in the input layer will still create noticeable changes in the output layer. And once this condition holds true, then the gradient will be able to latch onto it and improve it. So this is the intuition. But it's only related to training deep nets. Even if scientists had figured this out many years ago, neural nets would still not be useful.
So can you say something, I mean, it sounded like when you talk about applying these linear transformations stage by stage, it starts to sound like something, like there's this area of random matrix theory, where we can understand the, say, eigenvalues of random matrices. And this is getting a little bit technical, but this property of things decaying to zero is a kind of stability where some things are sort of stable in that they converge to zero, or unstable in that they explode when you repeatedly apply a transformation. And what it sounds like you're saying is that the eigenvalues of these random matrices need to be around 1. Is that fair?
That's very fair. This intuition is precisely correct. We definitely care about the size of the signal. If our eigenvalues are too small, if our matrices are too small, they will make the signal disappear. But it is also true that if our matrices are too large, then they will introduce so much instability into the system that learning will not be successful. And so there is this sweet spot of scale for the random initialization where things work well. And so in practice, when a practitioner wants to train a neural net on a real data set, the scale of the initialization is one of the most important parameters they need to worry about.
Now, Ilya, you're famous for several different things, but one of the things you're famous for is your work on recurrent neural networks, which are extremely deep. And did this intuition about what happens with a 10-layer neural network arise from your work on RNNs?
It's all very connected, yes. RNNs are neural networks which are adapted to deal with sequences. So the way they work is that imagine you have inputs coming in, you got a new input coming every second, and you've got a new hidden layer coming in at every second which you compute, and you use the same connections, you use the same weights to compute the new inputs. So it's a bit like a dynamical system. It's responsive. It's very interesting. And so with recurrent neural networks, you always want to train them on long sequences because that's the interesting case. Unlike neural networks, where even a 2-layer neural network can be interesting, a recurrent neural network with 2 time steps is not interesting. And so you're naturally pushed to this regime where you have long sequences in recurrent neural networks, and then the scale plays an absolutely crucial difference. The effects of the scale of the initialization in recurrent neural nets are magnified compared to those of the deep neural net.
So Ilya Sutskever, working at Google, some really interesting ideas.
Yeah, I really love talking to Ilya. I feel like I learn like many new things every single time I talk to him, and I just so many insights. He's so enthusiastic. I just really love talking to Ilya.
Definitely. So that's all for us this week. I'm not Ryan Adams, but you are.
I am Ryan Adams, and you are?
Catherine Gorman, I think, still. It's only been half an
true.
hour. So we'll be back in 2 weeks, but that doesn't mean that you should be a stranger. You can send us your questions and comments to thetalkingmachines@gmail.com, or you can tweet us at, and stay with me here, TLKNGMCHNS. It's just our name, no vowels. Thought it was clever. So see you next episode. We're going to be talking with Kevin Murphy, also of Google, about his research and also the textbook he's written. So stay tuned. Stay with us.